Hi everyone, welcome to my channel. I've got the Heathkit Digital Design Experimenter out, and I've been experimenting with shift registers, trying to wrap my brain around the shift registers and using them with the Arduino. And the good thing about using the Design Experimenter is you have control over the individual bits one bit at a time, instead of jumping right into hooking up your shift registers to an Arduino and trying to grasp what's going on with the sketch and the shift registers at the same time. This allows control over the individual bits of information and just allows you to more easily absorb what's going on the basic level. So here I have two shift registers with 16 LEDs connected to them. We can get in closer here. So it just so happens that I have a bank of 8 green and 8 blue, because I didn't have 16 of each. And what I'm looking at here is my ability to shift in one bit at a time into the very first shift register. I know here's an example with the Arduino. If you're using shift out, someone has taken the time to put together a function that's going to handle 8 bits or a byte of information at a time and shift them for you behind the scenes into the shift register. This here is the basic level where each individual bit gives you the ability to shift them. This gives you the ability to shift them individually into the shift register and out to the LEDs to give you a better appreciation of what's going on behind the scenes compared to, upper level programming with the sketch and the Arduino. So I have, this is the very first shift register right here. So I'm shifting bits of information one bit at a time into this shift register. Once this is full, it has a pin that allows you to then cascade to another shift register. So the excess bit that gets shoved out of this shift register, because it can only hold 8, will then be the very first bit that gets clocked into this next shift register. Now you have to keep in mind that you're shifting data into these shift registers, but then there's another signal that then makes that signal available to the outside world. It's in there, but then you have to have an additional signal to make it available to interact with the outside world, in this case in the form of turning on an LED. So it's something like this in block diagram form. I only have the very first shift register, but this last storage location here also can tie in, if I can get this to right, into the next shift register to the left. So here we have the data, and the data is either a 1 or a 0. This looks like a clock, but if you just had the data is only going to get shifted into these registers on the leading edge of a clock pulse. So it's not going to do anything on the falling edge. It's only on the leading edge of the clock pulse. So if this was a constant high, every time this clock pulse, which would be going alternately high and low, every time we get to the leading edge of the clock pulse, it would look at this as a high, and it would start, if you just left it as a high, it would start shifting in ones into these registers. So you have to keep in mind that the data is not always going to be high or low. It's going to be clocking in some pattern. That's where we start getting into the idea of what we want these LEDs to do. So the programming, not only you have to think about how you're shifting this data in, but then if you have in mind certain patterns that you want the LEDs to start flashing in, that's where the programming comes in, and how you get these patterns to show up exactly when you want them to show up to the outside world. Because, so if there was a high here, and then we had the rising edge of a clock pulse, a 1 would be shifted into this register. So the way the register works, or a flip-flop in here, once this clock pulse, once this data goes low, it doesn't react. That 1 is stored in there. But there's another register here that's connected to the outside world. So if there's a 0 currently in here, this LED, in this case, we have the anode hooked up, it's common cathode. This is not going to turn on until there is a high here. So we'll have a 5 volts, and then when there's a ground on the other side, because they're common cathode, this will then light up, current will flow and this will light up. But this high, which is actually a representation, a digital representation of the actual voltage, which is 5 volts, it doesn't become available here until we clock it. So we have to clock it in. The shift clock shifts data into these registers, but then the register clock shifts the data from here out, where it then becomes available to the outside world. So in any particular point in time, we could have the data, but it's not available yet to the outside world, because the previous data that we have, if in this case a 0, is not biasing on or not turning on this LED. So now we can start shifting, information in the form of 1s and 0s into these registers. Say that's the pattern. We could do it in chunks of 8, and that's what that shift out function does that we can use. But in this case, with just the digital trainer, we have to shift all these individual bytes in 1 bit at a time. It's going to take 8 clock pulses to get all these in, and then a single register clock will shift simultaneously all of these out and then make them visible to the outside world, where they can then turn on these LEDs at a time. So they're here, and then once we get the rising edge of the register clock, whatever is in here is then available out here. And then in this case, let's just fill these in. These 2 will be on, this will be off, this will be on, this will be off, this one will be on, this one will be on. Remember, the 1s represent plus 5 volt level, and this one will be off. So this is the pattern that we would on just 1 clock pulse. So if we take a quick look again at the pin layout for the 74HC595, we can see here all the pins. We have the R clock, register clock, and then we have the shift register clock. We have serial data in, so the data is entering in serially, and then we can output that data parallel or simultaneously. All these outputs are available on the rising edge of the register clock pulse. The shift register clock is what is used to shift the data in on pin 14. So that's the theory, but let's take a look at a physical circuit and how we go about clocking in data. So this switch here, that's low, that's high. So that's 5 volts, that's low, that's 0 volts. that's the 5 volts is a representation of the logic level 1. 0 volts is the voltage representation of logic level 0. So here, physically, I can alternate between a logic 0 and a logic 1. Here, I have my shift register clock control. Let's get in here. There we go. Did put a label on it. So here's the shift register. So this is connected to B. So this is 0, and because it's B naught is the default, it's this little pulse momentary switch here. So when I go like this, that simulates the rising edge of a clock pulse. Here is the register clock. Same thing. This simulates the rising edge of a clock pulse applied to the register clock pin on the chip, on the 74HC 595, 74HC 595. So let's take a look. So visually we'll be able to see what's going on with the LEDs. So again, remember, we can shift data into these shift registers, but visually, the representation visually isn't going to be there until we shift that data out with the register clock to make it visible, but it is in the chip. So let's start off with, so we have 0. So there is a 0 being applied to the serial input of the very first chip. That's going to get shifted in when I simulate the rising edge of this shift register clock. So if everything went according to plan, I just shifted a 0 into this position here. You know what? Since I already have this pattern available, let me start shifting this pattern. Well, the very first, so now see the first bit that I shift in is going to be the most significant bit. So I already put a 0 in, so the 0 will end up here. So I have to go this way when I'm thinking about the data that I'm shifting in. So I have the 0 in. Believe me, it's in there if I do this properly, but you don't see anything. I could make it visible, but I'm not. I'm going to shift all the data in one bit at a time and then simultaneously make them available to the outside world where we will see it visually with the LEDs. So the next bit of data that I want in is a 1. So I have to turn on, I have this switch, the serial data in. It's now a 5 volt signal, or a logic 1, and now I shift it in. So that's in. I want another 1 in, so I'm keeping that there, shifting it in. Now I want a 0, shift it in. Now I want a 1, shift it in. Now I want a 0, shift it in, and then 2 more 1s. So shift in the 1, shift in the 1. Now, if everything has gone according to plan, I should have this data in this pattern in the 2, well, I'm sorry, I messed up. This data is going to be in, let's get this correct. Oh yeah, this is going to be in the very first shift register. Just lost my mind there for a second because I have the ability to shift in 16 bits of data. So I have filled in the very first shift register. So we will see this pattern only on the 8 LEDs here because I haven't shifted in 16 bits of data. So I do that by using this register clock. So when I clock this, the rising edge will then make this data shift into these registers, which then become simultaneously available to the outside world. So the LEDs should light in that pattern. Let's go. 1, 2, 3. There we go. Let's see, what do we have? We have 0, 1, 1, 0, 1, 0, 1, 1. The LEDs are lit with the, remember that this is just a light representation for human interpretation. The logic levels, voltage levels that are in the shift register. So 5 volts represents a 1, and that then physically turns on and lights the LED, which we're saying a lighted LED represents binary 1. And the off LEDs represent logic level 0. So now what I can do is I can either shift 1 bit in at a time, but what I can do is I can take this pattern here, this pattern, and simultaneously shift it over into this register. So it's going to take 8 clock pulses to do that. So I'm going to shift it over by shoving in or sending in zeros, 8 zeros through this register, which again, what I have, let me get another whiteboard. So what we have is two 74HC 595s. Now their register clocks are tied together and the shift register clocks are tied together, but the data is only, the initial data is only going through this very first shift register, and once 8 bits have filled this up, because it only can hold 8 bits, the overflow is available to this 74595. So then it will get clocked into this shift register. So whatever comes out of here will then start getting shifted into this. So I have to do, I have to shift in 8 bits of zeros. It's going to take 8 leading edges of clock pulses. I will shift out the existing data from this register and shift it into this register, and then the rising edge or the leading edge of the register clock will then make them all available to the outside world. So that pattern will shift from here to here. Now visually, that's something that starts messing with your brain too, because it becomes available simultaneously, but it will make it look like magically everything was here and then all of a sudden was here. But you have to realize that behind the scenes, the data was being shifted, but it just wasn't available. So for this particular circuit, you would approach it, the programming would be different if the topology, or if you had this hooked up completely differently. You would have to approach it from a programming perspective differently. You know, if you had individual, if the shift register and the clocks you kept separate for each chip, and you were trying to control them individually, you could probably then do all types of elaborate patterns that maybe would be restricted if you were hooked up this way. So there's all types of variables here. So now let's shift this pattern over to this group of LEDs, or this pattern from this shift register into the second shift register. So again, nothing will change with this approach, I could do it individually to get all this stuff to shift, but let's go to 0 here on the serial data in, and then 8 of these shift register clock pulses. 1, 2, 3, 4, 5, 6, 7, 8. So essentially we have 2 storage blocks of storage registers here. We have 8 for the shift registers and then 8 for the registers that are connected to the outside world. So we've now shifted, we've turned these, we've changed all these bits to 0. So these are all zeros now for the very first shift register. Let me put the zeros in there. 0, 0, 0, 0, 0, 0, 0, 0. So there's all zeros there, but we still have the old data available here in these registers that are lighting these LEDs. This pattern is now in the registers of the second 74,595, but they're not going to be shifted to here until the next register clock. So let's see if that actually happens, if I haven't messed anything up here. So shift, there we go. The zeros in the very first register have been shifted into these registers, resulting in all these LEDs being turned off. But we used 8 clock pulses to shift the former pattern that was in here, got shifted 1 bit at a time into the second register, and then on the rising edge of this register clock then became available to the outside world. So we have this pattern available to the outside world. It's also in this register, but this is the first register's existing condition. So let's see if they match. Yeah, we have 0, 1, 1, 0, 1, 0, 1, 1. So what we can do now with the shift out is start forming whatever patterns of on and off LEDs we want, but with 8 bits at a time. You could do it also without using that and go in there and start manipulating these zeros and ones, but that function there allows you to do it in the form of 8 bits at a time. So let's start looking at a circuit that's hooked up. Well, we can take this and hook this up to the Arduino. So now you can see I've got the Arduino hooked up with the sketch loaded to produce this scanning LED pattern, and I've just taken the 3 control lines that were hooked up to the digital trainer, and I'm now driving these 3 control lines, the data in and the register clock and the shift register clock, with these 3 output pins on the Arduino. So when you look at this visually, you're thinking, okay, I've got something's going like this, but that's what it looks like visually. But internally, we're shifting those ones and zeros in to make it, to give us this pattern here. So you can get confused as to what exactly is going on behind the scenes. So I hope this video gave you a little better insight into how shift registers work and what's going on behind the scenes, how we're manipulating logic levels, zeros and ones, and how what goes on behind the scenes is then manipulated at a higher level with the sketch that I've loaded into the Arduino to drive these LEDs into this particular pattern here. I'll include a link in the description. Again, this particular sketch I did not write. Again, why I tried to reinvent the wheel. And I'll include a link in the description to this sketch where you can try it out yourself. So, hope you found this video helpful. Please like, subscribe, and/or comment, and thanks for watching.